Okay, so first, Geert, I want to thank you for inviting me to give a talk. So you mentioned you were having trouble finding someone who is reusing published data, and well, that's something we do all the time in paleomagnetism. So I'll talk a bit about that. So here's my title, and I was at Utrecht University before till June when I finished my PhD, and I started a postdoc last week here in Milano. Um, so I'll start with talking about paleogeography and how we use paleomagnetism to reconstruct that. So maps of the past, paleogeography provide the framework for actually studying many aspects of Earth's evolution, for example, geodynamics, but also climate evolution and the evolution of fauna and flora. And paleomagnetism serves as the main quantitative tool to do so, because paleomagnetic data allows you to constrain the past locations of tectonic plates and continents relative to the Earth's spin axis. So in this example, you see the classical Pangea reconstruction by Alfred Wegener more than a century ago, whereby all the continents are reconstructed relative to each other in this supercontinent that you're all familiar with. But with paleomagnetism, you can position Pangea and all the continents that were part of that relative to the Earth's spin axis. And then you can already see that it gives you a way to determine the paleolatitude of all these, of basically every location on Earth, which is, of course, an important parameter for climate and for paleobiology. So I will tell you now a little bit about how paleomagnetism works for those of you who are unfamiliar with it. So paleomagnetists go into the field and sample a different kind of rocks often with a drill. And here on the left, you see examples of paleomagnetic samples. And when you demagnetize those samples in the lab, you try to obtain a past recording of the magnetic field that was stored in the rock by magnetic minerals. And that hopefully gives you the direction of the past magnetic field at the time those rocks were formed. And that direction that you can measure within these samples is then often expressed in two angles, which is the inclination and the declination. So the inclination is the angle with the horizontal, and this angle is directly related to the paleolatitude. And the declination is the deviation from present day north, and that can tell you how much this locality has rotated relative to present day north. So with these angles, you can already see that can provide you a way of reconstructing that location or that tectonic plate that you're sampling a locality on in past times. All right, so we don't collect just a single sample in paleomagnetism. This is where it becomes a little bit more complex, because the Earth's magnetic field is changing on time scales of tens, hundreds, thousands of years. And to obtain an estimate of the time average magnetic field that you need to reconstruct paleogeography, you want to average those shorter term variations. So that's why paleomagnetists go and sample and take a lot of samples from different horizons of different lava flows or dikes or sedimentary beds. And you can see that there is a kind of hierarchical structure in the sampling, and this is where the data of paleomagnetism becomes a bit more complex. So you obtain a set of paleomagnetic directions measured from each sample, and to estimate to use this data for making a paleogeographic reconstruction, you often convert these directions to a past pole location, so location of the geomagnetic pole, and then average all those different measurements to obtain an estimate of the time averaged magnetic field. Yeah. So here you see an example. So one of these horizons or a lava flow or a dike is what we call a site in paleomagnetism. So per site, people typically collect multiple different samples. So it's shown here in light blue. Those are averaged to one site level pole position, and then all those site level data is then again averaged to a single best estimate of the past pole position relative to your sampling location. So you can see here that there are different steps whereby data that is collected in the lab is averaged to higher hierarchical levels. Okay, and then there's even a next step. So you can see that paleomagnetic data analysis can be quite complex. And a central concept to reconstructing paleogeography using paleomagnetism is apparent polar wonder. So if you see here on the left, if you imagine a imaginary continent moving north from 60 million years ago to 40 million years ago to 20 million years ago to the present day, relative to a fixed pole coinciding with the Earth's spin axis, then if you would collect paleomagnetic data from the rocks of those different ages, then you would see the past paleomagnetic pole position wander away from the present day North geographic pole, so back in time. And this is not because the paleomagnetic pole has moved in time, but because the continent itself has moved. At least that was the interpretation in the 50s, and we still believe that. So and this path of successive pole positions is then what we call an apparent polar wonder path. And when using these apparent polar wonder paths, we use the prime assumption in paleomagnetism that the past average geomagnetic pole coincides with the geographic pole. Okay, so and if we now use data from basically all major stable continents on Earth, and we use a relative plate reconstruction model, so here you see a Pangea fit, for example, then you can actually obtain a so-called global apparent polar wonder path that relative to a chosen reference continent gives you the moving position of the paleomagnetic pole. So for this, we often use Africa because it has been the most stable continent, supposedly for the last couple of 100 million years. All right, so how do we then use this to reconstruct global paleogeography? So here on the top left, you see this apparent polar wonder path again. So if we now want to reconstruct Pangea at 250 million years ago, so at the beginning of the Triassic, we first have to use a relative plate motion model, which you see on the bottom left. So that's kind of like the Alfred Wegener style Pangea reconstruction. And then we rotate the entire reconstruction, so the entire configuration of continents and tectonic plates, such that the paleomagnetic pole coincides with the Earth's spin axis again, which you see here on the right. And that gives you an absolute plate reconstruction, positioning all continents relative to the past Earth spin axis, and thus giving you paleolatitude for basically all locations on Earth. Right. That was the maybe a bit technical background of paleomagnetism. So now we go into how we use the actual data to construct this. So conventionally, apparent polar wonder paths, so those that are used to reconstruct paleogeography, are computed by averaging a set of paleomagnetic poles. And I will shorten them here to paleopoles. And basically, each study, so each scientific publication, used to provide a single paleomagnetic pole estimate. And to construct these apparent polar wonder paths, we typically use a running mean approach, whereby we average all those different paleomagnetic poles, so here in red, to the running mean poles shown by yellow diamonds. And it's important to remember that each of these study level paleomagnetic poles, here highlighted in red again, consists of a whole bunch of site level data, which then again consists of a bunch of samples per site. Okay, but in this approach, each paleomagnetic pole was always weighted equally, regardless of the number of sites that was used in that original study, and also regardless of the uncertainties of each pole position. So that is, of course, like that is not what we want. That's a huge drawback of this approach, that we're not propagating any of these uncertainties. So how does that typically look like? How does that use of published data look like? So basically, since the 1960s till a couple of years ago, in these constructions of apparent polar wonder paths, there were always tables like the one shown here, where you have paleomagnetic pole positions, here shown with their latitude and longitude of different rock units, with an age estimate without uncertainty, and a 95% confidence region, but these were not used in any way. So in these traditional apparent polar wonder path constructions, no age uncertainty was provided, and also the uncertainty on each pole position was not taken into account in any way. So what does that look like? So here you see a plot of the apparent polar wonder path by Torsvik and others, and you see all the individual pole positions plotting around there. And you can see that there's quite a large spread, suggesting that not every individual study really provides a very accurate estimate of the past pole position. So what we wanted to do was to incorporate extra information in the construction of the apparent polar wonder path, as well as first order uncertainties in the age of the sampled rocks and in the paleomagnetic data itself. So alternatively, you can either compile all the different site level paleomagnetic data, but to do this for all published data of the last 50 years would take years and years and years. So we took a shortcut whereby we used the published pole positions and their statistical parameters to simulate the real data again, to approximate the real data again. And this way we can assign a larger weight to larger data sets, and we can propagate these important uncertainties in terms of age uncertainty and the uncertainty in paleomagnetic pole positions. And this is what we call then the pseudo VGP. So it's the simulated site level data. So to do this, we locked ourselves up a couple of years ago with 14 people and computed and went through more than 600 publications, went through all the databases, collecting all these paleomagnetic pole position data and their parameters. And after applying some stringent selection criteria, we computed a new apparent polar wonder path from more than 13,000 different paleomagnetic sites. So you can imagine compiling more than 13,000 data points by hand from papers going back to the 60s would take a lot of time. And here you see a map with like the spatial distribution of where all that the data comes from. So after seeing the classical table, this is a snapshot of the data table that was used for our new apparent polar wonder path. And you see that there are way more parameters, and we have documented all age constraints and provided comments on the reliability of each data point. So this is already quite a step forward in reusing data and documenting what was actually provided by the original authors and what was explained in the papers. Right, and here you see this new apparent polar wonder path. I will not go in the details, but it's nice to note that our paper was published only a few weeks ago with this new global database. All right, and then even the next step that we've been developing for the past year is compiling or constructing apparent polar wonder paths from real data. So just for North America, for the Cenozoic, we again went with more than 10 people and compiled from databases like Magic all the individual data points from 39 studies. And you can see here an overview map where all those localities were, and age distribution of the compiled data. And what is interesting is that here in figure B, you can see that the magnetic field variations are that large that it's quite hard to see a signal within this cloud of individual data points. But if you use a clever algorithm, then you can see that for North America, the pole position moves gradually away from the in this case, the South Geographic Pole, showing the plate motion of North America during the Cenozoic relative to the Earth's spin axis. And with this compilation of data on the site level, rather than the whole study mean level, we managed to compute an apparent polar wonder path with a 1 million year resolution. And before using site level data, the highest resolution that was achievable was 10 million years. So we increased the resolution of these paths 10 times by reusing all the published data and by diving into the existing databases and in the original papers where needed. All right, so then we put this compilation, so 31 locations with 1,700 sites back into the MAGIC database, so that now it's available to everyone. And of course, some of the publications that we compiled were already in this database, so that was quite easy to do. But since many of these data infrastructures have been developed only so recently, the problem is often in paleomagnetism that papers and data sets from the 60s, 70s, and 80s are not available at all in one of these databases. So large efforts are needed to make sure that these are added to those databases. But that's something for the future. Right, some take-home messages. So paleomagnetism provides the main quantitative tool to reconstruct paleogeography, and conventional paleomagnetic approaches did not incorporate many first-order uncertainties. But by reusing published data and using existing databases and data infrastructures, we can better quantify a polar wonder and better constrain paleogeography using paleomagnetism. And as I showed you, we can even go to a 10 times higher resolution than before by reusing these data and statistical parameters. So making all paleomagnetic data findable and available is crucial for improving these statistical methods and for increasing resolution of future models. So that's probably easier to do for any new data becoming available, but there's also a lot of work of adding existing data to these data infrastructures. Right? That was my talk. Thanks for watching.